Bioinformatics.
Hi, and welcome to Lecture 5. This time we'll be talking about BLAST, which stands for Basic Local Alignment Search Tool. And of all the tools that we probably talk about this semester, this might be one that you are familiar with because it's used really at all levels in genetics and molecular biology, both as a web-based tool as well as a command line tool. The reason I'm going to talk about this tool is because, as we addressed earlier, the amount of DNA and protein sequence in public databases are huge, and they're growing more and more every single day. Last time I looked, the NCBI protein database had around 54 million different proteins, and the nucleotide database, is off the charts. We talked about using alignment to find regions of homology between known homologous sequences, and they're really great at doing that. But they're very slow, and while they find really the best possible alignment, there's no way to scale that to the databases as large as we're dealing with now. And so we need to cut corners and cheat a little bit and use something that's a lot faster. And BLAST is really a tool that's universally used for this purpose. BLAST is a heuristics tool. What that means is that they take shortcuts, but they're not guaranteed to find the absolute best possible solution. It's kind of funny. This is probably one of the few pieces of software that dates all the way back to 1990 and is still in use today. If you look at the paper where they published this, it's been cited 57,000 times. And I would bet at this point there's a lot of people that don't even think about citing BLAST because oftentimes you're using BLAST just kind of as quality control, and it's possible that this should be cited 3 times as many times. So how does BLAST work? How is it different from what we've done before? So in a nutshell, and again, this is going to be a very basic explanation, BLAST takes your query sequence. So for those of you that haven't blasted, basically you have a database with a bunch of different sequences. Think about all the sequences in NCBI gene, for example. And you have a sequence that you got from an organism and you're like, hey, I wonder what gene this matches. Well, you can query the database with that sequence. So the query is your sequence of interest, and the database is really the target, if you will, or contains the targets. And so we take that query sequence that we want to search with. Think about just like a Googling term or something. And similar to how Trim-O-Matic worked, it breaks it up using a sliding window. So this is a sliding window with 3 bases here, length of k, in this case k equals 3. It takes the first 3, then it takes 2 to 4, then it takes 3 to 5, and all the way through until you end up with every possible 3 base pair window across the whole sequence. Then all those little tiny pieces are now a lot easier to deal with. And so for every single sequence in the database now, those little 3 base pair fragments get mapped onto them. And so BLAST basically looks for how many sequences out there share some of these what we'll call words, because there are a set number of letters. How many of these sequences share some words? Here's an example of one that shares 2 words. And only keeps instances where there are target sequences that share words from the query sequence. So you can dump big chunks of your sequence database from further analyses this way. Next, words are scored for their similarity. So very similar to scoring matrices we've seen before. You could get full points, in this case 18, if every single letter matches the query to the target. And decreasing values for different levels of mismatch and deviation. Some threshold will say, you know what, we're not even going to count it as a hit anymore. Don't need to get into too much detail with that, though. Just know that things you learned about scoring matrices still hold. Whatever scoring matrix you pick, here's Blossom 62, a very popular one. Your results are only contingent on that scoring matrix being appropriate. Okay, so how does this work? So we've got our query sequence. We break it up into words. And then within our database sequence, we try to see how many match. Now, once we get matches, BLAST is going to try to extend these matches further out. So it goes, okay, well, I know there's a good word here and a good word here. How much similarity is there in between them, though? Because conceivably, if this really is a homolog, there's probably going to be, even if there's mismatches, some homologous regions in between these words. So this is where the stage called extension happens. And eventually you'll end up with whatever the largest, highest scoring kind of extended island of similarity or sequence is what will maintain and be reported in your BLAST result. So how does it know when to stop extending? It's, again, very similar to kind of what we've been dealing with. There's a scoring matrix associated with this. But let's say our query sequence was the quick brown fox jump, and the target sequence that it found in the database was the quiet brown cat purr. So what's going to happen is every time you get a mismatch, you're going to step up 1 from 0. And there'll be some cutoff number where you're finally cut off. There's enough mismatch. We're not going to count it anymore for extending. And so to illustrate this, our score from 0 right now is 0. And we've got matches, 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 matches. Here's a mismatch. We'll up the counter to 1. Here's a mismatch. We'll add another one. Now it's 2. Oh, wait, these two are the same. Not a mismatch. We'll go back down 1. Okay, they still all match. We're back to 0. But now we've got 1, 2, 3. All mismatches here. We've got another mismatch. We count down again because we had a match. And then 2 mismatches, and we hit 5. And if 5 is our cutoff, this is where that extension would cut off. So if the phrase was originally the quick brown fox jumps over the lazy dog, we would not include that because we already hit our cutoff point for our extension. Okay, oftentimes what happens once you have your big region where you've had your extension, that's also then when an actual specific local alignment is conducted as well. So that's where you get gaps and all sorts of things inserted as well, or indels inserted. And what's interesting about this is during the local alignment now, even though you already went through your extension and said, here's the island that we're going to look at from now on, your local alignment can then extend even farther beyond that. So particularly in instances where there's lots of indels, your local alignment following the BLAST extension can increase the size of the fragment again as well. And what's interesting is you can end up with multiple local alignments from the same sequence or even chunk of sequence. So here we see an example where there was a really high scoring alignment here, here, and here, all from the same sequence. What's interesting about BLAST and confusing when people first start using it is each one of these alignments are treated separately when BLAST reports your information. So if you have a really closely related homolog of a sequence you're looking for, your top 3 hits could all be fragments from within the same gene, from the same organism. And so that's just something to be aware of. There are lots of different flavors of BLAST. It all depends what type of data you're starting with and what type of data you want to look at, so the database type. So if you're starting with nucleic acid data and you're looking at a nucleic acid database, you would use BLAST-N, N for nucleic acid. If you're starting with protein data, whether it's explicit, you have the amino acid sequence, well then you could use T-BLAST-N if you're going to a nucleotide database. You could go to another protein database using BLAST-P. You could also start with nucleic acid, but translate it into protein data and then blast that against either a protein database or a conceptually translated nucleic acid to amino acid sequence database as well. And this one can get complicated because you've got 3 possible reading frames for every set of translation. So for this, you'll have, for your query, you'll have 3 possible reading frame translations, and then same for every single target in your query, in your database. So these things can get really interesting. Now, if you're looking at really, really big stuff or doing lots and lots of BLAST runs, you might even go for MegaBLAST, which uses larger word sizes and only tries to find identical hits. So it throws off that first step where you have your words hit and look for certain similarity scores using a matrix. You just look for long strings of hits right off the bat, and it's just kind of, is it there or is it not? And this is great with nucleic acid against large databases because it's a very fast algorithm. But again, it requires a perfect match before you can start that extension phase. If you want a little speed, but also a little less exactness, discontiguous megablast uses a greedy algorithm, which we talked about in the last lecture, isn't always great at making the best decisions for the long term, but does make good decisions over very short stretches. And so it's good for finding things that are similar but not perfect matches to your query. It actually will use fuzzy words in some cases, where it will make some letters not actually need a match. So you can think about it's being analogous to wobble in codons. This can be quite slow relative to megablast, but can be faster than some of the other flavors of blast. Okay, so let's say you did a blast, and here is one possible blast output. Typically, your blast results will give you a bunch of blast results, all of different scores and of different subjects. So here is what should look familiar. This is just kind of a basic alignment. We've got our query sequence, and then we've got one of the subjects or targets from the database. We've got a couple things that we can see here. We see that there are lots of matches. There's a couple mismatches. I don't see a lot of indels or any indels whatsoever. And then we've got some good information here that I'm going to talk about that comes along with this. We've got the e-value, which is basically the likelihood that given the size of the database and the size of your query, what is the likelihood that you would just by chance, with random factors, end up with a alignment or blast result that had this same score, that looked just like this. And so here, the chance is 3 times 10 to the negative 109. So we're pretty certain that this is not just a chance of fate, that these sequences are that similar due to just random chance. We can also see just some general alignment information. The number of matches versus mismatches. So there were only 6 mismatches here based on the identities. There were 0 gaps, so no indels. And then again, sequence data can come in 2 forms, right? You can have the forward or the reverse sequence. You can also, or think about the template versus the coding strand. And so here it's telling you, based on what's being kept in the database versus your query, that these two are both on the same strand relative to one another. It didn't have to reverse complement one of them. That typically does not impact many things that we're doing analysis-wise, though. Okay, so what do you really care about in there? The e-value is one of the big ones. So again, that's really, you can think about that as being your stats for how likely it is to make a mistake. If we had an e-value of 1, that means just by chance we would expect a blast result to have that score in our database. So we don't want to blast something, get an e-value of 1 and go, that's our match right there. No, typically we want something a lot smaller, like an e-value of 10 to the negative 5th or lower, something along those lines. People also, you'll see out there, will use the e-value to sometimes judge whether a sequence is homologous or not, as opposed to paralogous. And so that can be problematic, as I mentioned when we talked about alignment. But oftentimes you're not always left with, perfect solutions when we're working with data these sizes. So you'll see in the literature out there that greater than 10 to the negative 5th for an e-value, we're fairly confident that it's a homolog. Once we get below negative 5, we're not sure. And then once we get to 1 or even 10, we're not certain that it's really something we want to use at all. We really don't think so. So the final thing I'll end with, and you guys kind of did this at the very end of the last lab, is multiple sequence alignment. So we talked about alignments pairwise for the most part, but then at the very end we saw that you could actually line up sequences from multiple things. And so the types of alignments that I talked to you about, the NW and the SW, could be used for multiple sequence alignment with that matrix. But the problem is when you go to 3 or more things, that table becomes 3-dimensional and really computationally heavy. So similar to how BLAST cuts corners, there are also heuristic alignment algorithms as well. They'll typically do things to save energy, like looking at just the overall identity or similarity between two sequences, and then taking the two that were most similar and just aligning those pairwise. Then taking the consensus of those two and aligning a third one pairwise and so forth. So there's lots of little tricks to aligning multiple things. So I just wanted you to be aware of that since we did talk about that in the last lab. Next up, you're going to be doing a practice lab with BLAST and starting to explore how that can be used with large data sets. And we'll be doing that in person. So if you have questions while you're doing the lab, I'll be there to help you. Thank you.